Hello, good day everyone. I am Samuel Junior A. Pinales, and for today's topic, we will be tackling about the electrode potential, or also known as standard reduction potential. So, what is a standard reduction potential or electrode potential? It is a measure of the ability of a half cell to attract electrons towards it. So, as you can see at the picture, it is a sample of the standard reduction table. We only have copper and zinc, but in real, there were a lot of elements written there. So, next, the more positive the half cell's electrode potential, the stronger the attraction for electrons. So, the higher or the more positive the half cell's electrode potential, the stronger or more, the greater the attraction of electrons. Then this tendency for reduction. Reduction takes place at the cathode, and also cathode is located at the right part of the cell reaction. Next statement, it says that standard reduction potential of copper half cell is more positive compared to zinc. So in this statement, we need to go back at the table or the picture above and observe the picture. We have zinc and copper there. The cell potential of copper is positive 0.34 volts, while the zinc has a cell potential of negative 0.76 volts, which is copper is way more positive than the zinc. So, zinc will become the anode. Anode, it is where the oxidation takes place, or where you lose electrons. So, anode is located at the left side of the cell reaction. Remember that reduction is the gain of electron and oxidation is the loss of electron. Next. Here, we are given a picture for the sample on how to get the electrode potential. In calculating the electrode potential using the standard state condition, the formula given are E anode cell is equivalent to E note. Again, the formula given are E note cell is equals to E note cathode minus E note anode, or you can also use the E note cell is equals to E note reduction minus E note oxidation. So from the problem that was given lately, we have zinc and copper. Since copper is way more positive than zinc, so we will be using zinc as the anode and copper as the cathode or the reduction. Now, next, we need to substitute the given numbers. E note cell is equals to E note cathode. Our cathode again is the copper, which has a positive 0.34 volts. Next, minus E note anode. Our anode is the zinc, which has a negative 0.76 volts. So, it will be written as positive 0.34 minus negative 0.76. Since there were two negative signs near each other, we need to change it into positive sign, a basic rule of math. So, it will become positive 1.10 volts. The final answer for the standard state condition. You can also use the second formula, which is E note cell is equals to E note reduction plus E note oxidation. By using this formula, you need to change the sign right away. So, you need to substitute all the given numbers. Reduction or cathode, we have the copper, which has the 0.34 volts, plus the oxidation or anode, which is zinc, that has negative 0.76 volt, but since you are using this formula, you go directly into the positive sign or the positive 1. So it will become positive 0.76, and you're going to add all of that and you will get the positive 1.10 volts in the overall cell reaction of copper and zinc. Below, we are given the half cell equation at anode and cathode. The half cell reaction can be interchanged, can be reversed. It differs on what is the position or what is the role of that cell reaction. Is it anode or cathode? Is it reduction or oxidation? So, in anode, we have zinc. Since anode is the oxidation, zinc will be losing 2 electrons. That's why it will break down into zinc solid, 2 zinc and 2 plus aqueous plus 2 electrons. It was breakdown because it loses 2 electrons. Next, the cathode, which is the copper, it will remain since it is the standard state or the standard potential. So since it is the cathode or the reduction, it gains 2 electrons from its reaction. So the half cell equation for the copper will become copper 2 plus aqueous plus 2 electrons will produce copper solid. I hope you get that. Next, we'll be moving for the exercise. Calculate the standard cell potential of the following electrochemical cells. Here we are given the cobalt element and the silver element. First, we need to know the standard cell potential of cobalt and silver. In knowing the cell potential of cobalt and silver, we need to use the standard reduction potential table. So here, after we get the cell potential of the cobalt and silver, the silver has a cell potential of positive 0.80 volts, while the cobalt has a cell potential of negative 0.28 volts. Since it is the silver that is way more positive than the cobalt, so silver will become our reduction or the cathode. And since the cobalt is negative, we'll be using it as the anode or the oxidation. Remember the half cell reaction is change depends on its role or position. So since the silver is used as cathode, it will remain the same, like silver aqueous plus electron, it will produce a silver aqueous since only 1 electron was. Next, anode oxidation. Since it is the anode, it will lose electrons, so it will break down from the cobalt solid to cobalt 2 plus aqueous plus 2 electrons. So in calculating this standard state condition of cobalt and silver, we need to use the formula. E note cell is equals to E note cathode minus E note anode. So our cathode is the silver, which is positive 0.80 volts, minus the anode, which is the cobalt with negative 0.28 volts. Again, since the basic math rule, when there is two negative signs near each other, we need to change it into positive sign, which will cause it to add all of it. So we will, after adding all of it, the cell potential of the overall cell reaction for cobalt and silver will have positive 1.08 volts. So here, the table shown standard reduction potentials at 25 degrees Celsius. So this is the table you're going to use, and you're going to find the cell potentials of each element. So it is a measure of the ability of half cell to attract electrons towards it at 25 degrees Celsius. The pressure is 1 atom, 4 gases, and the concentration of electrolyte is 1 mole. The sign of E naught changes when the reaction is reversed. As what I've said lately, if the reaction is reversed, or if the reaction is reversed, or it has its rule, if it goes from cathode to anode or something, its E naught changes. Next, changing the stoichiometry coefficient of a half cell reaction does not change the value of E naught. So let's proceed to the next slide. Here, the example. First thing that was stated there, that E naught will change if its reaction is reversed. I'm so sorry for the noise. So look at the third one. It is different from the first two reactions. It was reversed, and the cell potential, or the E naught of it, was changed from positive to negative. And next, look at the first two reactions. It was the same, and the E naught was the same, nothing changed, but the coefficients of it was different. The first one doesn't have 1/2 of it, but the second one has, and the number of electrons that was involved. But since it was said at the first one that changing the stoichiometric coefficient of half cell reaction does not change the value of E naught. Okay, let's proceed. Now we are going to dig down. We are going to tackle the standard hydrogen electrode, or SHE. It is made up of a platinum electrode immersed in an aqueous solution of hydrogen with 1 mole and bubbled with hydrogen gas at 1 atom pressure and temperature at 25 degrees Celsius. It is quite familiar because I have stated earlier that the standard reduction potential comes from and has 25 degrees Celsius with a pressure of 1 atom, 4 gases, and a concentration of 1 mole. So this SHE is the one where all of those standard reduction potentials or cell potentials came from. So since mahog nga siya ang himong kanang nahimo nga basihan, siya ang gipares-pares sa uban nga elements para makuha tanan nga standard reduction potentials. Okay, let's proceed. Standard hydrogen electrode, the direction of half reaction of SHE depends on the other half cell connected on it. The cell notation for SHE is either, when it is a cathode, maguna ang iyang H plus ay AQ, tapos H2 gas, and the PT sulit. If it is the cathode, it depends kung ang iyahang gipares nga element is cathode ba or anode. So mag-differ pagkaana niya. And if anode siya, ang solid PT may maguna, mag-interchange sila, like i-reverse lang nimo ang ilahang position. So magstay ang H2, tapos ang PT wag ang H plus or hydrogen 1 is mag-interchange. In either case, if bisagon sa pangabali-balian aniya or cathode or anode man na siya, ang iyang cell potential or ang E naught niya remains 0. Okay, so that was the standard state condition. This is the formula on how you get or calculate the electrode potential using standard state condition. Again, the formula is E naught cell is equals to E naught cathode minus E naught anode, or you can also use the E naught cell equals E naught reduction plus E naught oxidation. Next, refer to the least standard reduction potential. Oxidation agent is located at the left of the half cell equation. Reduction agent is located at the right of the half cell equation. So the example was given there, the picture. So as it increases the strength of reducing agent, it goes from positive up to negative. Down to negative. So from positive, where it is a strong oxidizing agent, the positive one, and down to negative one, which is the strong reducing agent. So the more negative the value of E naught, the stronger the reducing agent. The more positive the value of E naught, the stronger the oxidizing agent. Next, we have this exercise. Arrange the three elements in order of increasing strength of reducing agent. Increasing strength. So from the oxidizing agent down to reducing agent. So we have X, Y, and L. The L has positive 0.85 volts, while the Y has negative 2.87 volts, and the X has negative 1.66 volts. So what do you think is the order of it? So since L is positive, it is a strong oxidizing agent. So it will be the first one. Since it was said that increasing strength, so we will increase. So next is the X, which has the negative 1.66 volts. And lastly is the Y with negative 2.87 volts. That is the order of the increasing strength of reducing agent, L, X, Y. Okay, proceed. Now we will be using the Nernst equation. You will be using the Nernst equation if you are going to calculate the E cell for any chosen concentration. Remember, the standard state condition has 1 mole on it. All of the elements that was given has 1 mole on it. But here, in using the Nernst equation, you will be facing a lot of chosen concentration. It depends on the chosen concentration. That lower in any chosen concentration, maybe it is lower than 1 mole or higher than 1 mole. So the formula that you are going to use, there are 3 formulas. There are 3 formulas you are going to use. First is the E cell is equals to E naught cell minus R. R stands for the gas reaction or standard gas, and T stands for the temperature, divided by the N. N stands for the number of electrons that was involved in the reaction, and F stands for the Faraday's law. You multiply it by the log of the product over the reactant, or also known as the reaction quotient. Next, the next formula you are going to use, or you can use, is the E cell is equals to E naught cell minus 0.0257 divided by N, the number of electrons involved in the reaction, multiplied by the 2.303 log of the product divided by reactants, or also known as the quotient reaction. Next, the third one, or the easiest one, E cell is equals to E note cell minus 0.0592 divided by the number of electrons used or involved in reaction multiplied by the lag of product divided by the reactant, or also known as the reaction quotient. So here, the product divided by reactant, or the reaction quotient, is equals to Q. So we are going to ease up the things, and we will what do you call that? We are going to make product over reactant to letter Q. So the final formula for it is the E cell is equals to E note cell minus 0.0592 divided by the number of electrons involved multiplied by the lag of Q, or reaction quotient. Okay, here we are going to have the example number 1. Calculate the E cell for the following cell. Here we are given the elements, or the overall cell reaction of zinc and copper, where zinc has a mole of 0.02 mole and copper has a mole of 0.40 mole. So first, before you use the Nernst equation, you will be needing to calculate first at the standard state condition. So first, you have to do the overall cell reaction of copper and zinc, which is zinc solid plus copper 2 plus aqueous, producing zinc 2 plus aqueous plus copper solid. So you are going to determine which is the cathode and anode, or the reduction on oxidation. So for you to know which one is the cathode and anode, you will be needing to observe first, or see it through first from the standard reduction table. So since copper is way more positive than the zinc, so it will be our cathode, positive 0.34 volts, minus to our anode, which is the zinc, that has negative 0.76 volts, and you need to sum up it all because two negative signs were near each other, and you need to change it into positive, and you will have then positive 1.10 volts. Or you can also use the easy one. E note cell is equals to E note reduction plus E note oxidation is equals to positive 0.34 volts plus 0.76 volts. You have changed it already from negative to positive sign. So same answer, positive 1.10 volts. Next, proceeding, we are going to use the Nernst equation already. So the Nernst equation formula is E is equals to E naught minus 0.0592 divided by the number of electrons involved in the reaction multiplied by the lag of the reaction quotient, or the reaction quotient. It is a product over reactant. So next, you need to substitute all the given. E is equals to positive 1.10 volts, which is the E naught of copper and copper and zinc, minus the 0.0592 divided by 2 multiplied by lag, and substitute the amount of mole for Z and or zinc, and the amount of mole for copper, 0.40. So first, in calculating this, you need to calculate first the log of 0.02 divided by 0.40, or the log of quotient reaction. After you have calculated the log of quotient reaction, you need to multiply it from the negative 0.0592. And after you have multiplied it, the answer of the multiplicate the answer of the answer so first, for you to calculate this, you need to for you to calculate this, you need to calculate first the log of quotient reaction, which is the log of 0.02 divided by 0.040. After you have calculated that, you need to multiply it to the negative 0.592. The answer of that is you are going to divide it to the number of electrons that was involved in the reaction, which is 2. Why 2? Because there were only 2 electrons present in the reaction of zinc and copper. So after you have calculated that, the answer or the equation will become like this. So the E note will remain, which is the positive 1.10 volt minus the negative 0.385. Since after that, you need to change the sign because the 2 negative signs were near each other. You need to change it into positive 1 and add it all. So the answer will become positive 1.139 volts for the 139 volts using the Nernst equation. Next, so that is the answer for the Nernst equation for copper and zinc with a non 1 mole concentration. So next, we are going to talk about what is using Nernst equation at equilibrium. So here note, no net reaction occurs. Q is equals to K. So there are no net reaction occurs. So it will be constant or what. So next note is the E cell is equals to 0. So we don't have any E cell here. It will become 0. So let's proceed. Same formula will be. It is the same formula we are going to use, but there are some changes. There are some changes. Just like as the E cell is 0 already, and there is no net reaction, so the quotient reaction will be changed into K, which is constant. So let's proceed. So substitute all the given. So we will substitute E cell into 0. It equals to E note cell minus the 0.0592 divided by the number of electrons involved in the reaction multiplied by the log K. So E naught cell, it will become E naught cell is equal to 0.0592 divided by N multiplied by the log K. Wait for a minute. So after you have substitute the given numbers, you need to transfer the 0.0592 together with the log of constant to the left side. So it will become 0.0592 divided by N, or the number of electrons involved in the reaction, multiplied by the log of K, or constant, is equals to 0, or is equals to the E node cell. Equals to the E node cell. So after that, you will be computing it already. You will be calculating it already. So let's proceed to the example for you to understand it more. Example number 2. Calculate the equilibrium constant, or K, for the following reaction. So our elements are copper solid plus 2Aj of AK, producing C copper 2 plus 2Aj solid. So here, using the formula of the equilibrium, E cell is equals to E naught cell minus 0.0592 divided by 2, or N, divided by N, the number of electrons involved in the reaction, multiplied by the log of constant. Next, you need to substitute all the given. E cell will become 0, is equals to E naught cell. E naught cell, this is the you're still going to use the standard state condition and the Nernst equation. So the standard, I'm so sorry again. Cu copper 034 and AJ EJ 80 2 minus it, so AJ 80 minus 34. So yeah, so in getting the E cell, you need to use the standard state condition, where its formula is E naught cell is equals to E naught cathode minus E naught anode. So after you have collected, or you have gathered the E naught cell, you subtract it to the 0.0592 divided by 2, which is the number of electrons that was involved in the reaction, and multiply it to the log of K, or the log of constant. But first, you need to transfer the 0.0592 divided by 2 and the log of K to the left side, which will cause that the 0.46, or the E naught cell, will remain at the right side. After that, you need to divide the 0.0592. You need to divide the 0.0592 divided by 2 divided by 2. Okay, 0.0592 divided by 2. I'm so sorry. 2 divided by 0.0592. So you will be having 33.78. 33.78. You will be having 33.78 78. After that, having that 33.78, you need to multiply it here at 0.46, or the E note cell. So 33.78 multiplied by 0.46. So it is 15.53 or 15.54, round off, which is here it is 15.54. After that, you need to the log constant. The log constant. Okay. After that, you already have the 15.54, which is the sum up or the equal of 0.0592 divided by 2 multiplied by the 0.46. Next, you will be getting the log of constant, and then you will be getting the log of 15.54, and the answer will become 3. The answer is 3.467 times 10 raised to the power of 15. So that is how you going to calculate the equilibrium using the Nernst equation. I hope it's clear. Okay, let's proceed. Now, for my second topic, it is the spontaneity of redox reactions. This topic is really easy, so it's just that you need to pay attention because it's kind of tricky, but well, I know you guys, you can make it. So, what is a spontaneity of redox reaction? A spontaneity of redox reaction is a type of reaction in which there is usually the release of energy where the electrons are transferred from anode to cathode. Remember, anode is where the oxidizing agent takes place, and cathode is where the reducing agent takes place. So let's proceed. Steps in taking this. Steps in taking this, or in calculating this. First, find the cell potential of reduction and the cell potential of oxidation using the half reaction table. So, if you are given the... So, you need to go back to the half reaction table and find the cell potential of reduction and the cell potential of the oxidation. And the given equation, E naught reduction plus E naught oxidation to get the sum of standard cell potential, which is the E naught cell. So the formula here will become E naught cell is equals to E naught reduction plus E naught oxidation, or the cell potential of reduction and cell potential of oxidation. And then identify if it is spontaneous or not spontaneous. So here are the problems. Sample problem number 1. Predict whether or not Pb2 plus can oxidize Ai solid or Cu solid, or copper solid rather, under standard state conditions, and calculate the E naught for each reaction at 25 degrees. Okay, so I have so next sample number 2. Predict if Zn2 plus can oxidize if Zn2 plus can oxidize Fe2 plus or Mg2 plus. Calculate E notes for each reaction. So here. So thank you guys for listening. I hope that you gather some information and gain knowledge on this lesson and lecture of mine. Again, my topics is all about the standard reduction potential and the spontaneity of redox reaction. Thank you. So here guys, this is the calculation of the sample for the spontaneity of redox reaction. The sample problem is predict whether or not Pb2 plus can oxidize AI solid or copper solid under the standard state conditions and calculate E cell for each reaction at 25 degrees. So the first one, I'm just going to simplify it. So the cell potential of Pb2 plus is negative 0.13 and the AI is negative 1.66 while the copper is positive 0.34. So for PB and AI, the PB will become the reduction since is it is not that negative, it is a lower amount or the lower number than the AI. So AI will be our oxidation. So here is the calculation for PB and AI. So the formula is E cell E naught is equals to E naught reduction or cell potential of reduction and the cell potential of oxidation. So our reduction is the PB, which is negative 0.13, and our oxidation is the AI, which is negative 1.66. So we are just going to add all of that, so the answer will become negative 1.79, and it is not spontaneous, a non-spontaneous reaction. So next, for the second one, we have Pb and copper. Since copper is way more positive than Pb, so it will become our reduction, and Pb will become our oxidation. So again, substitute reduction is the copper, which is positive 0.34, and our oxidation, which is negative 0.13, and sum it up, we will have 0.21 volts, which is a spontaneous reaction. So next, sample number 2. Predict if Zn2 plus can oxidize Fe2 plus or Mg2 plus. Calculate E cell or E notes for each reaction. So the E cell potential of Zn2 is negative 0.76, the Fe2 is negative 0.45, and the Mg2 is negative 2.37. So first we're going to calculate the Zn2 and Fe2. So Zn2 will be the oxidation since Zn2 will be the oxidation, it's way more negative than the Fe, and Fe will become the reduction. So here calculation using the formula E cell or E naught is equal to cell potential of reduction plus cell potential of oxidation. So our reduction is negative 0.45 plus the negative 0.76 for oxidation, and we will have the negative 1.29, which is non-spontaneous. And next, for the Zn2 and Mg2, since Mg2 is way more negative and way more greater as a reduction agent, it will become our oxidation. And since Zn2 plus is a great or a great oxidizing agent, and we will be having it as our reduction. So our formula, E naught or E cell of the cell potential reduction plus cell potential of oxidation, negative 0.76 plus negative 2.37 will be negative 3.13, which is a non-spontaneous reaction. So I hope you have gained some knowledge, guys, and thank you.